All right, very well. Well, morning, everyone. Welcome to the next installment of the JKMRC Friday morning seminar series that take place here at the Indrupili Lecture Theatre, as well as online, which is the case today. So my name is Katerina, and myself and Karina are the co-hosts of the seminar series and are taking turns introducing the speakers this year. On behalf of the University of Queensland and the Sustainable Minerals Institute, I'd like to respectfully acknowledge all traditional owners and their custodianship of the lands on which we all meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country, and we recognize their valuable contributions to Australian and global society. It is an absolute pleasure to introduce our today's speaker, who very graciously stepped in at the very last minute when Philippa, the originally agreed presenter, fell ill. So thanks to everyone for understanding and accommodating as much as possible. So our speaker today is Brenton Crawford, who, after studying structural geology and geophysics at Monash University, otherwise known as Monash Mafia, right? Spent several years consulting in mine geology, structural geology, and geophysics for PGN Geoscience, and predominantly in exploration. Brenton has also worked as a geophysicist and data scientist for MMG Exploration, working on nickel, copper, and zinc projects, as well as new project generation. And in 2015, Brenton co-founded Solve Geosolutions, Australia's first exploration and mining-focused data science consultancy. And then later in 2019, Brenton co-founded Datarock, a computer vision technology company geared at building productionized image and video analysis solutions for exploration and mining. And Brenton currently serves as Datarock's Chief Operating Officer. There we go. I also know that Datarock is the name of an electronic music band from Norway, and we will find out during the talk if Brenton is part of the band or not. Today's presentation is on a topic near and dear to me and is titled Combining Core Imagery and Computer Vision to Extract Quantitative Geological and Geotechnical Data. Take it away, and please let's welcome Brenton.
Great, thanks, Katerina. Thanks for the nice introduction. I'd worked a lot with Katerina in our past lives as consultants, so it's good to see you here. So, welcome everybody. Happy Friday, and thanks for letting me come and speak at one of these great seminar events. So today I'm going to be talking mainly about what we do as a business in terms of how we extract data sets from core imagery. I'm going to focus on just the humble core photograph for this talk, albeit we do things beyond that. And I'm going to try and give you a whistle-stop tour of what deep learning is and how it works, as well as then jumping into a bit of a case study as well. Before I go on, I have to acknowledge some of the great people we have at Datarock. We have a really great machine learning software engineering team, along with a bunch of really talented geologists, most of which are listed there. And I also like to thank Agnica Eagle for allowing us to present some data from their Fosterville deposit. Just before I get into the technical nitty-gritty, just a little bit about us. So we're a mining technology company. We're based in Melbourne and Hobart, and we have people in every capital city except Perth, despite most of our business coming from Perth. That's not on purpose. It's just easier to find technical people on the east side of the country. We have about 29 staff currently, mainly composed of software engineers, machine learning engineers, and data scientists. The business itself is kind of in three parts. We have an applied science team, which was formerly that Solve business that Katerina mentioned, and they work on everything across the mining chain, from greenfields exploration all the way through to plant process optimization type problems. All of our data scientists are geoscientists first. We have a machine learning team that really drive a lot of the work we do in the AI space. And we have a cloud-based image processing platform that turns imagery into data. And I'll talk to you about how you can apply that type of technology to get really useful data sets out of your core imagery. So a little outline of the talk today. I've already talked about who we are, so I probably shouldn't have that in the right order. But we'll talk about computer vision deep learning 101. I'm going to do my best to explain this very complex kind of bit of science in a very, very short space of time. So bear with me. Talk about what's good about doing it this way, versus how we've done it in the past. And then we'll jump into the Fosterville case study and talk about what we've specifically done at a really amazing deposit on a really large amount of data. I think it might be easier, Katarina, if people hold their questions to the end, but if anyone's got a really burning question, we can potentially do it during. I'll let Katarina, you can decide what you want to do with that. So away we go. So I guess I just wanted to show visually, I guess, what the point of us is in terms of that our platform offering. Everyone's got core photos. A lot of people are now starting to look at them in some sort of, in the cloud and things like that. But what are they actually good for? Well, we would argue that they're a very dense source of data that are really good for a bunch of things. And we would also argue that they are still the most underutilized data set that people have at their operations. They cost next to nothing to collect. There's obviously lots of high-end scanning systems coming onto the market now, which produce amazing data. And our argument is that that's great, but you need algorithms to extract information out of them that can transform imagery into answer products. And at the end of the day, as geoscientists, we want answers. We don't want more numbers. And the idea is when we put these two things together, we can create these deposit-wide data sets. Here we've got some things we'll talk about more in this talk, some alteration from a deposit. This one here's quartz vein volume. We've got RQD on the bottom left and a lithology weathering model on the bottom right. So these are the things that we really want to get to. We want answers on our drill holes that can drive our 3D models. Why did we, I guess, start this business? The main reason was that we spent a lot of time building 3D models, OBK models, GeoMet models for companies. And the quality of the data going into those is always really quite a challenge. Numerical data sets are really good, but a lot of important data actually still gets logged by people looking at the drill core and recording their observations. And if we don't get those things right at the beginning, it can really affect things in a negative way all the way through a very long life cycle of a mine. So the problem as we see it is that when we were building these models, log data was increasingly sort of not making it into the actual OBK models we were building. And the reason for that was that a lot of log data doesn't have an audit trail. Somebody makes an observation and then it goes into a database, right or wrong. And the consistency and quality that is well understood that, people are great at lots of really good things, but they're not really good at seeing the same thing when they look at a piece of rock. That's just who we are. And it's not a criticism of geologists, of which I am one. But I know that the way we see things just changes a lot, and that's the way it is. And what happens is that people want to rectify this, so they want to do relogging, but relogging is very expensive. Sometimes the core is gone or sampled. And the thing about the way that manual logging works is that it locks us into a model. So we get model locked because it's so much of an effort to drag core out and log it again. So what we're saying is log data is really good, but what if there's a different way, a better way to actually get that kind of log data out of the imagery rather than doing it in the traditional way we've been doing it, or augmenting that normal process. The idea, I like to show this, the OKW pyramid here. The idea is that, we're suggesting that not that geologists and engineers don't need to look at rocks, but they can often offer a lot more value to an operation working higher up this pyramid. And the really call it data mule kind of data sets, counting fractures and measuring things can often be or somewhat automated or augmented. So the idea is not to replace geologists and engineers, but to allow them to kind of do what people are better at. Okay, so diving into some of the technology that sits behind the work that we do. It's called computer vision, and I'll try to unpack a bit about what we actually mean by that, as well as algorithms built on deep learning. And yeah, I'm going to try to make this quick and painless as possible. So So the word computer vision gets thrown around a lot, but really it's a blanket term for a large field of study that's just is trying to help computers to see things. It sits within the field of AI, and it's one of those interesting sciences that I think people a long time ago thought we'd have this sorted out by now. But it's extremely difficult to teach a computer how to see the way that we see. Part of that is because we don't really understand how we see to some degree. And so, interestingly, we've had some really big leaps and bounds come on recently about how we can use computer vision. And I'll go into a little bit of what's happened to allow that. So computer vision sort of sits across, lots of these commonly bandied around words. So why now? Why can you build a business now on computer vision a lot more easily than you could in the past? Well, the reason is that you need some things to come together to allow that. The field of computer vision has been around for a long time. The key thing that's happened, in recent history is that we now have unlimited compute, essentially, that's available to us in the cloud. That doesn't cost that much anymore. We have sensors and data that are just in our lives so much more than they used to be. We all walk around with a camera in our pocket now, which wasn't the case just even a few years ago. And the key thing that really helped us is that these algorithms that computer vision are built on have really come on in leaps and bounds, driven by some of these very large technology companies, generally in their midst to try to understand more about the data that you're giving them through your social media. But they actually are really good at looking at rocks as well, luckily for us. The other thing here I'll draw your attention to is this plot, which is the number of yearly publications on AI overall. And you can see that it's, as of about 2016, it's going near vertical compared to what it was in prior years. Another question we get asked a lot is, well, how good is computer vision versus a person? And that's a complicated question. It probably does vary a little bit, but a nice example of that performance is this plot here. This is based on a very large open file data set called ImageNet. It's got 14 million images in it, 1,000 classes, everything from an apple to a backpack to a dog and a cat. And this plot we're looking at here is the performance versus year, and then the model type is listed on the colored bars. In yellow are non-neural network related models. In blue are the neural network related models, and the red one there is human performance. So you can see that for this particular task, which is identifying classes of imagery, you can see that we transcended or passed human performance back in sort of mid-2014. And that's still going down. It's 2017 is a long time ago in deep learning, so that number is still coming down again now. And so the answer is, depending on the task, computer vision can be significantly better than a person. But there are still things that we're better at as people. We have very complex visual systems as people. So how does a deep learning model actually see something? I am going to do my best to sort of make that a very simple concept, but essentially we have this thing called a deep neural network. It's filled with these layers of neurons, which are these white circles. Those neurons have these connections, which are often called activation functions. And the idea is that each one of these neurons has kind of a filter on it that can see something, can see some pattern or texture. And the way it works is that we feed an image in the front. It will be decomposed in such a way to fit into this network. And each layer is going to see something about that image. Generally, early layers will see something simplistic about the image. That might be a gradient or an orientation of a gradient. And as we dig deeper into the network, those individual neurons will start seeing more complex concepts about what that image could be. So you can see that in the second layer here, we're looking at things like eyeballs and noses. And if we keep going down the layers, we start to see these really creepy ghost faces. So now the network's looking at the whole structure of a face. In reality, there's lots more than 3 layers in a deep neural network. But the idea is the deeper the network, the more complex the things it can understand are, with some caveats. So the idea is that this is very analogous to what we do and how we process imagery. And the reason deep learning is so powerful is because it's a deep network and it can see kind of more complex things. That's my best attempt at summarizing that. So how do we train a deep learning model to actually do something that we care about? The first thing we want to do is get some annotations. Annotations come in the form of, they could be a polygon within an image, looking at a vein. It could be just a classification of an overall image saying this image contains a vein. We want to show these trained images to a network, and the network will not know what to do. It's untrained. It will give you the wrong answer. But what will happen is the network can receive a wrong answer and change itself to become closer to the correct answer. And we'll go through this in a moment. And then we need to repeat that millions and millions of times. So we give that network an opportunity over and over and over again to adjust itself to produce an answer that is more in line with the training it's receiving. The idea is that network is going to restructure itself, and it's going to end up being very powerful at doing the thing you're training it to do. It has lots of levers to pull to change itself. And this is actually analogous to how our brains learn as well. So when we're learning something new, we're making connections, we're destroying old connections, we're strengthening the things that matter, and we're weakening the things that don't matter. It's basically what's going on here. Okay, so just to go to a very well-known data set, it's called MNIST. MNIST is a database of 60,000 images of hand-drawn numbers, very similar to what you might draw in a postcode digit on a letter or something like that. And what we can see here is I've got a great animation from 3 Blue 1 Brown, which is an amazing YouTube channel, which I would highly recommend if you want to learn more about this. And basically what it's showing here is we're taking an image of a hand-drawn digit, we're feeding it in the front of our neural network, and we're lighting up certain neurons, and those activations between the neurons are also being activated at the same time. And when we get to the end of the network, we're getting this kind of weighting applied to the numbers 0 through 9. And so what's happening here over and over again with different numbers is that if we put it, we put a 0 through, we're getting weightings on 0, 3, 4, 5. That's wrong. So the network needs to change itself to stop weighting 3, 4, and 5 and keep weighting 0. And the idea is that you can see the image flows through from left to right, and then it flows backwards from right to left. And that's the network updating itself to try to not get that same incorrect answer again. And so we're doing this over and over and over again. This is essentially showing an untrained network having data fed through it and producing either very incorrect or a somewhat incorrect answer. So keep that in mind. And now we're going to switch to what does a neural network look like when it's actually trained properly. So now we're looking at the number 9. Number 9's flowing through, it's lighting up some of our neurons. Those neurons are then sending activations to other neurons, which are then lighting up and seeing some other feature of the number 9. And then it flows through to the end and lights up the number 9. So the model's very sure that's a 9. That's a network that's been trained correctly and is now doing the right thing. So you can see that the thing here that's interesting is that different layers are seeing different things about that 9 that make it a 9. So that's kind of the critical thing here that's that we're doing with this neural network. It's a complicated beast that can change itself in complicated ways to produce very complex behavior based on training. Okay, so enough about hand-drawn numbers. What about some rocks? Let's look at, what could we see using this kind of technology if we're looking at something like a vein. So here's an image of a vein. If we're talking about the word classification, what that really means is we're taking an image of any shape or size and we're saying, what class is it? So in this case, we use this a lot. We move these little squares down the core and we say, what class of whatever you care about is inside this image? In this case, we've got a vein, so the image class is vein. This is the easiest thing to do with these kind of deep learning based models. If we move up the kind of complexity scale, we get to what's called semantic segmentation. This is essentially where we're phrasing to the model, show me all the pixels that belong to the class vein. The model has no understanding of what an instance of a vein looks like. It just says, okay, anything that you think is a pixel that's in a vein, color it. So you can see here that we have veins that are overlapping and crossing each other. None of that's understood. We could just do the vein volume or something like that. If we move up the complexity scale one more time, we're at object detection. Object detection is we're trying to predict a bounding box around an instance of a feature, in this case, a vein. And you can see that these little boxes allow us to kind of count veins. There's lots of complexity about, veins on top of veins on top of veins, and which veins are one unit and which ones are offset by those. But essentially here, the model's trained to know what one vein looks like and find all of those instances, but it can't see what the exact boundary of the vein is. And if we go to the very hardest thing to do, we call it instance segmentation. And instance segmentation is where we're trying to find every instance of a vein and map its boundaries at the pixel level. And so that's the most complex thing that we can do, and it's what we use a lot at Datarock to do all sorts of things, from the geotech stuff all the way through to the geological things. And the instance segmentation type models are the ones that have really come on in leaps and bounds in the last sort of 5 to 8 years. So what does this training, or what do the outputs look like when you're doing these kinds of analysis on an actual piece of rock or a row of core? So you can have these kinds of models that predict polygons around features within the core tray itself. So in this case, the top row is kind of how we calculate a lot of our kind of basic, just detect everything in the row models. So you can see here that in blue, we've got cylindrical pieces of rock. In that kind of burnt orange color, we've got kind of out of place or incoherent pieces of rock. We've got empty space in the pink. We've got a core block in the green. So this is actually an instance segmentation model that's been trained to recognize instances of these certain types of features. If we're talking about classification, sometimes we might have a model where we actually just want to classify the rock sequentially down the core. And here you can see that we've divided those rocks up into squares, given them a class, and colored them by that class. And at the bottom, we've actually got a semantic segmentation model for quartz. So this model is just saying, find me all the pixels that belong to a quartz vein. Okay, so let's watch a model learn how to see. I can't control when this starts and ends, but I'll talk you through the iterations. So what we're actually looking at here with this image is the output of a neural network at each iteration of the learning process. So basically, it's counting up through the iterations. It's getting smarter and smarter about what a vein looks like. And eventually it's going to converge and then stop and go back to zero. And I'll talk you through kind of from zero up to the end. But the idea here is that you can see there's a bounding box. You can also see that the pixels themselves are being picked up because it's instance segmentation. So here you can see the model starts by looking for regions that are likely to contain a vein. And you can see the probability or confidence scores are quite low. The model is finding these things, but it's not super sure yet. And then after it gets sure enough, it starts to say, okay, well, I'm pretty sure there's a vein here. I'm now going to try to find the pixels that belong to that vein. And as we count up iterations, that is that process we just previously went through, where the model is changing itself over and over and over again to be better and better at the task that you're training it to do. And you see at the end, it just says, I can't do any better, and that's it. So why do we use deep learning for this kind of task? Well, it's because core imagery is really variable. Unless you have a system, the Catarina used to work with a lot called CoreScan, where the imagery is very standardized and everything's collected in the same way, or HiLogger would be another good example. When you're dealing with core photos, everyone's used a different camera, the lighting's different, the images are all over the place. But the nice thing about deep learning is because these models are based on experience, as long as you let the model experience the variation, there's not much of a reason why that shouldn't still work. So even though we have some boxes that have 2 images, some that have 3, some that are taken outside, inside, as long as we show the model all that range of variability, the model can accept it and still do a good job. So that's why this is so powerful for this task. So what do most people do with their core photos? Well, they look at them sometimes. They log from them sometimes. They use them as a historical reference of what was drilled. But the world is changing and people are starting to see a core image as a numerical data set, not dissimilar to geochemistry or geophysics. And that's a good thing. What do we do with core photos? So on the geotech side of things, there's obviously things you can and can't do with a static image. But we often produce things like RQD, frequency, fractures, orientation, fracture analysis, joint set number and analysis, weathering models. We're just starting to get to the point of being able to do some of the rock mass characterization systems, or at least significant parts of them, like GSI, RMR, and Q. And on the geological side of things, it's really, I've listed some things that are common asks, but to be honest, it's choose your own adventure. So if you can see it in the image, a model can be trained to detect it using a model like this. So that's kind of the power that you can get out of this humble photo, which would have cost next to nothing to collect. And you can buy the sensor for this in any department store. Okay, so moving on to the case study. So it's going to be at a deposit called Robbins Hill, which sits within the Fosterville sort of mine. I'll go through a little bit of geology and then talk about a lot about the outputs and how they've sort of helped as part of this review. So back in 2019, when we were very, very young, in terms of not having a heap of this done, Fosterville engaged us to sort of help them out in the core shed. They had hit this beautiful deposit called the Swan Zone, which was full of gold, but they knew that wasn't going to last forever. And they were looking to create efficiencies in the core shed and in the core logging system. So they want to reduce the cost, they want to improve the consistency, they want auditability in their data collection, and they also want to create some new types of data sets, particularly around veins, that's going to help them with their ore body knowledge. And since we started that, we've logged more than 6,300 holes, more than 1 million meters of core, which has been pretty cool. If you don't know about Fosterville Gold Mine, it's just east of Bendigo in Victoria. And it's quite a world-class deposit. If you take a long section through the deposit, we've got this Swan Zone, which I mentioned down on the left here. This case study holes are going to come from a deposit called Robbins Hill, which is sort of off to the north a little bit, and is kind of a current development for them. In terms of the drilling at Fosterville, they do a lot of drilling. Massive amounts of drilling. So you can see that back in 21, this 2022 number is just a partial bit of 2022. So it's the numbers will be much higher. But in 2021, they did 180,000 meters of drilling. This is their fantastic core shed, which looks like an Amazon fulfillment center. It's got, I think it's like 15 rows, individual rows. Core flows in a hole through the back of the shed, down a roller rack. It never leaves its roller rack, and then it flows out. And yeah, it's a fantastic facility, and you have to have something like that when you're drilling near on 200,000 kilometers of core each year. Robbins Hill itself, we've got some data, which is 438 diamond drill holes. And what we've done is we've registered that imagery in space, and we've produced some geotech and geological data sets. A little bit on the mineralization at Robbins Hill. So it's sulfide mineralization. It's in dilational structures, veins and faults. The mineralization itself is a lot of pyrite, arsenopyrite, and trace stibnite, glenus, sphalerite, and chalk. Yeah, let's get into let's look at some imagery. So here's a pretty typical core photo from Fosterville. It's taken using a great system actually created here in Victoria called Casper. It's just a DSLR camera with a really nice shroud, and just is a low cost, great camera. Gets rid of the glare. It's got a color palette, and this is probably what I would describe as a upper middle class core photo in terms of how good it is. It's probably 150 microns, and yeah, everything's controlled. So if we go through that, first thing we'll do to the image is we want to crop the rows out. We're going to then go in and crop out different kinds of rock. We're showing just one of the things we do here, which is find all those coherent bits of rock, but we'll do lots of other things alongside of that. Then we'll end up with this kind of analytics ready image, which is going to have all the rock that we need, but we'll get rid of things that we don't care about, like core trays and core blocks and whatnot, before we do some sort of data science or analytics with them. One thing that's really overlooked in core image processing is depth. And depth is an absolute wormhole of complexity, both on how it's collected at the drill and also how it's represented in the image space. We have things like core loss. We've got broken material, which takes up more room than it does in the ground, causing grief. And with Fosterville, they actually didn't record their depth information on their core photos. So all we had was where the hole started, where the hole ended, and whatever we could read off the rock itself. And so we developed a system that would allow us to read meter marks off the core itself, and have this kind of regression iterative process that would allow us to refine the depths until we were happy. So what we would do to start with is we'd say, okay, the hole starts here, the hole ends there. Let's measure all the bits of rock that we've detected with our deep learning, and we're going to add all those chunks of rock together, and we're going to suggest where we think meter marks could be. And you can see here that, if you look at 2014, you can see that we're nearly, 40, 50 centimeters off where 2014 meter mark is actually. And so what we need to do is tighten that up somehow with some detections on the core itself. So what we do then is we use a process called optical character recognition, and we would scan through these imagery and look for numbers that would pass some logic tests to be an actual depth marker. And those OCR would also have to be within tolerance or within some reasonable distance of our first pass predicted meter mark. And then what we could do is actually start to shift those meter marks up. Sometimes the meter marks were so far out that we didn't really know which one to use. So what we would do is we'd do this kind of iterative process. We'd catch some of the OCRs, we'd drag everything back into the right spot, and that would in turn bring other things closer to their correct spot as well. And then we would do it again. And essentially we would do it again and again and again until we stopped getting any more new OCRs being detected that were deemed to be useful. The thing that's really good about this process is we've actually got two answers about the way the world works now. So the geologists have told us how much rock is in the tray by the position of their meter marks. And we've also measured how much rock is in there because we've detected the fragments from the image. And the cool thing about that is we can finally give people some QAQC on their depth. So do you have too much rock in this interval, or do you have too little rock in this interval? And that's really powerful because you probably wouldn't be amazed to find that there's a lot of problems with depth in drill core, just as an industry. So then in our system, you can go in and you can fix the errors, modify things until it passes what we call the health check. That's a great thing. Okay, so it's a static image. You can't see inside the fractures, for instance. You can't see on the bottom of the rock that you're not looking at. There are limitations to what you can actually do with these techniques, but there are also some benefits. The benefits are that we can look at the pixel scale and we don't get tired, and we can look at millions of meters of core and process them in a few hours. The models are fluid, and as a geoscientist myself, the idea that you're stuck in a logging model because of a logistical problem is really not good. If you have a change in the way the world works, you should be able to change the model and apply it backwards on data, and that just should be the way things work. And you can do that with this kind of analysis because the imagery can have models applied to it in a very trivial way compared to dragging core out. It's consistent, it's auditable. We can show you why we called certain things. And you can also create data sets that are just not economical to log with a person. An example of that would be, we did a job looking at kimberlites. We were segmenting, phenocrysts of olivine. A person can count a little square of them. We can count the entire drill hole worth of olivines. So those are things that, they're new types of data because you can't make them with a person. That's just too much work. Cool, so let's talk about some geotech data. I'll start at the end in terms of summarizing all the things we've done at Robbins Hill, but we've done fracture classification, frequency spacing, we've extracted the dominant color, we've got the amount of broken rock. We're working on a model at the moment to characterize the size and shape of broken rock as well. We've got RQD, a few different methods for RQD, weighted joint density, joint roughness coefficient, joint set numbers, weathering degree, and we've got a GSI proxy. We're very close to getting to GSI. We just don't have the joint condition, so you can make some assumptions based on lithology to get a number. But what we're really going to is to produce partial GSI, Q, and RMR, and then allow the engineers to come in and add the data that we can't see from a static photo, and then hit a button and produce it. So as I mentioned, one of the benefits is this kind of scale of interpretability. So we're jumping around from an actual fracture to a row, to a full drill hole, to a full deposit. And we really can operate at the pixel scale, but at a scale that allows you to analyze an entire deposit, which is really one of the powers of this kind of technology. If we talk about something specific like RQD, it's one of the easiest things to make. All we need to do is segment all the bits of rock that are coherent and sound, and measure them, and bits that are less than 10 centimeters are classified as one thing, and bits that are longer are classified as something else. And the key thing with RQD is the main thing is your depths have to be perfect. If you have depth errors, then you'll never get the correct RQD because you'll start counting and stop counting at the wrong spot. And so one of the really interesting things we've found is when we've calculated this RQD is that if there are differences to the person logging, it's usually because we fixed the depths and then calculated it, and the original RQD was done on depths that had a problem. So that's a really interesting kind of finding out of millions of meters of this that we've produced over the last few years. Here's an example of some of the data. At the top, we've got our weighted joint density RQD. We've got a predicted RQD using the normal DIA method and incoherence, which is the amount of broken material. And then we have to produce this summary, we call it like a summary image. It's basically all of the rows of rock with the core tray chopped out, squished into a tube. So you can kind of see the changes in the colors and sometimes textures. We leave the core blocks in, but we also produce an extract of the actual RGB values as well. So at Robbins Hill, we produced about 11,000 intervals of RQD. Processing of that data takes about 20 minutes. All the holes just parallelize out in the cloud. So if you find a mistake and you want to process something differently, it doesn't take a long time. To relog RQD on this amount of data would be, it would be a 7-figure number if you were paying a consultant to do it, for sure. In terms of joint sets, we can see that we can look at these very detailed things on joint sets. So we can look at the shape, the roughness of the boundaries. We can fit ellipses to those features as well. And what we're doing here is fitting a JRC score to the bumpiness of that fracture. And then we can plot them on a great circle and actually measure their orientation. We can detect orientation lines as well. In this case, we're just looking at a artificial ori line in the green, which is at the bottom of the core, but we can detect the ori line and actually measure these open fractures with respect to them. One thing that's really interesting is that we can't do a joint set roughness calculation from a photo because you can't see into the fracture. But what we can do is measure how bumpy that joint is on where it intersects the outside of the core. And interestingly, it appears that from our testing is that this number actually holds up pretty well, but only on a lithology by lithology basis. So some lithologies, external bumpiness reflects its internal bumpiness in certain lithologies and not in others, which was really interesting. We can do joint set numbers. So we can do, if we don't have an orientation, like measure how curved the fracture is and also its alpha angle. And then what we do is we have this sort of entropy reduction system. We divide the water up into compartments, and we can move those compartments around to minimize joint set number score. And what we can see here is we've got curvature versus the core axis alpha angle. Each fracture is a dot on this graph. And you can see that we get a 2 sets plus random score here because we've got one compartment with more than 3 fractures and 2 compartments with 3 or less. And for this geotech interval, which is 3 meters long, we measured 88% of all the fractures that were present in that interval. Fracture detections themselves, this is a object detections type model. Here we're actually classifying the type of the break that we're seeing. And so we can look at things like disking in a really nifty way where we can look at disk spacing and curvature and all these other things. We can look at different kinds of rubble, broken material, and even multi-interface fractures as well. And the nice thing about this is we can use them to create frequency and spacing and all that sort of stuff, but we can also start to kind of produce slightly different versions of geotech data that you wouldn't normally get with a human logger. Here's some example data of what that looks like. We've got fracture spacing, fractures per meter, weighted joint density, and then we've got that same kind of graphical representation as well. Okay, so onto some more geological things. I wanted to show this example because it shows that image variation can be managed, even in historical image data sets that have a lot of variation in them. Here we're looking at 10 classes from Lithology model at Robbins Hill. It's been a while since I've presented this, but we've got a couple of vein dominant lithologies. We've got Crete. They actually, when they drill through Crete, they actually log that as a lithology. We've got a few different weathered zones, black shale, a few different intrusions and host sediments. And the one I'll draw your attention to is this center bottom square, where you can see there's like really 2 dominantly different looking imagery within that square there. So just to go back, these are actually predictions from the model. So these are little squares that have been predicted as each of these 10 classes. And you can see that the model is saying that this stuff up here and this stuff up here, down here, are the same class. And that's because the model was trained to understand that there are 2 very different kinds of imagery coming into this model. These imagery taken, that was really old, looked a lot more like the bottom stuff, and imagery taken with the newer systems looks a lot more like the top stuff. You can see how much better the quality is at the top there. Here's what the model looks like on the Robins Hill deposit. We've got our lithology model applied to 30 million 5-centimetre image tiles. It's applied to all the historical data, and it's being applied to new imagery as it arrives in the core shed. And it takes a couple of minutes to apply this model to new imagery. So the idea is that we're producing a lith log for the geos within the hour of the image arriving with us, and then they can log on that and use it to streamline their logging process. It's hard to see a lot here because it's sort of this interbedded sandstone sequence. So you see a lot of the interbeds here. You can see some of these yellow dikes. We've got the weathering units at the top there and some black shales in these maroon colors, if you can see them on your screen. If we zoom in on just one particular lithology, here we're looking at some intrusives. And these intrusives present really nicely in the core photos. They're often sericite altered and have this kind of nice yellowy green color. On the left-hand side in pink is the dike logged by the geos, and on the right is the dike predicted from the core imagery. You can see that they are very close together because the thing that we're looking for is quite easy, quite dominant, visually easy to see, I should say. To kind of talk about the scale of which you can do this, there's a bit to unpack in this plot, so I'll try to go through it sort of systematically, but essentially we're looking at a 500-meter drill hole. Excuse me. We've got the dominant color extraction on the far left, so we can see the weathered zone, and then we're in this sort of monotonous grey rock after that, plus or minus quartz. We've got the geos log from Fosterville, and you can see that there's a few different classes in there. We've got this kind of light blue sandstone. We've got the shales in grey, and we've got this interbedded. The light blue is an interbedded sequence, and then you've got these other columns, and those other columns are actually our predictions. And people sort of see this and go, "Oh my god, that looks so different." Well, the reason they look different is because we're actually logging at 4-centimetre scale, and we're logging every individual square as either a sandstone or a shale. So where the geo is lumping into an interbedded sequence that's light blue, we are actually finding every individual interbed. And so that might be a problem because it's way too detailed, but the idea is that it's judging every little bit of rock on its merit. And because people only have so much time, and because of the mine's requirements, they're only logging this in this sort of lumped way. What we can do then is lump our raw prediction, and we can say, okay, I'm going to go to 0.5 meter composite, 1 meter composite, and 3 meter composite. And this is something that was probably very common for Katarina to do when she was at CoreScan. You would have this really high resolution data set, and then people would say, make it worse, because I need it to look worse so I can actually use it in my model. The really neat thing about these machine learning models is that they also come with a confidence or a prediction score. And the nice thing about that is it turns a categorical data set like logging into a continuous numerical data set. And the nice thing about that is it actually makes it a lot easier to model with, especially in things like Leapfrog, where you want these continuous variables into your model. You can see here we're looking at the prediction of sandstone, the prediction of shale, prediction of quartz, and the prediction of LQ quartz, which is just a certain type of vein they have. And so you end up with this much more downhole geophysics type number, and that actually creates a lot of opportunities to model this in different ways. Okay, home stretch. So obviously, Robins Hill is a vein-hosted deposit, and veins are one of those things that are really time-consuming to log. So often when geos are logging veins, they're saying, okay, well, over this interval, I've got this number of veins or this density of veins. And the idea here is that, it's a nice dark rock with really nice quartz veins in it. It's actually really easy to see them in these RGB imagery. And so the quartz veins, obviously being the thing that holds the gold, they've been logged in some way, many different ways over the course of time. Different consultants have come through and said, oh, you must log them like this, or you must log them like that. So what we wanted to do was apply one modern understanding of quartz veins and apply the whole deposit with the same thing. So you're seeing from the same sheet when you're looking at old and new. We've done it in two ways. We've done a segmentation of quartz veins to produce things like count, volume, and density, as well as classification of quartz vein types as well. So we look at segmentation. This is really straightforward segmentation. It's just white quartz on a dark grey rock. And what we're doing here is we're saying, okay, what's the centimetre squared volume of quartz? You can see here a cross section through Robins Hill. There's a big fault coming through on purple, and you can see that you get a lot of quartz volume proximal to that structure. This is a semantic segmentation. If you use an instant segmentation, you could also say there are 14 veins in this meter. If you use instant segmentation, you could also say, what's the alpha angle of each of those veins? So seeing the rock like this and classifying like this opens up a lot of opportunities to log things that a person would not be good at collecting this type of data. If you ask a geologist, estimate me in centimeters squared how much quartz I have over this unit, that wouldn't be a very good number at the end. That would be my gut feel. Here's how it looks over the whole Robbins Hill deposit. And you can see these kind of west dipping structures in the quartz vein volume. These are actually the large fault trends that get picked out really nicely. This is a data set they didn't have previously. So that's really helpful for them. If you look at quartz classification, we've got 5 quartz vein types here. The exact nature of each of these quartz veins escapes me at the moment, but we have the extensional quartz veins, which are really large and really clean looking on the right. We've got these kind of shear veins and transtensional veins that make up the rest. And the idea is that we've divided the world up into these little 5 centimeter squares. And every time we get a square, we're saying, what kind of vein do I have in it? And then giving that class. So this is what it looks like if we look at it on the Robbins Hill deposit. So we've got grey veinlets, which are just kind of everywhere. We've got these red shear veins, we've got yellow extensional veins. And you'll see as well that we get these kind of west dipping structures coming out again. You're getting a lot of these big, thick extensional quartz veins around the major structures, which makes a lot of sense. And you're getting little veinlets everywhere. Cool. So just to hone in on that a little bit more, we've just picked a smaller number of holes here just to look at to make it a bit easier. But you can see that if we go and look at the predictions for each of those quartz vein types, or just 2 of them, I should say, we've got a quartz vein style A, which is blocky quartz, and then we've got quartz vein style B, which is a laminated carbonaceous quartz vein. You can see that we're just finding them up and down the holes. And what we've done here is we said, over every half of a meter, tell me what the dominant vein type was. So we're transforming that kind of raw prediction, which can look quite noisy, into something that is now a lot more kind of rational to interpret and model, which is, what is the dominant thing over this interval, even though there might be other things in there. Cool. So to summarize what was done at Robbins Hill, so we produced a lot of geotechnical data that's a lot better to interpret and more auditable. Lithology and alteration classifications, quartz segmentations and classifications. We've generated new ABK learnings and really hope to improve all the speed, consistency, and auditability for the very large amount of data they produce on a yearly basis. And we did a little back of the envelope. It's probably horribly wrong, but for the Robbins Hill deposit, all the data sets that we collected at the resolution we collected them, which is a bit crazy for a person to try to do, would take 50 people 1 year to log the same amount of data manually. So it's always good to end on like a shocking statement just for impact. But yeah, that's kind of our back of the envelope calculation. So yeah, that's it. Thanks a lot for having me. And yeah, Katerina, I guess any questions? I'm happy to hear them.
So much, Brenton. I think Zoom cuts out the sound of a clap.
I saw the claps happening, so it was okay. Yes. I got it in spirit. Yeah.
Very good. I think we all want to become computer vision scientists now. Do we have any questions in the audience? Yes, we do. And we'll get to the online questions in a minute.
Hi, Brendan. My name is Vladimir. Thank you for a great presentation. I really enjoyed how you simplified very complex process. My question: you show some results that the comparison between computer vision performance with human, where you compare the errors. The question is, if you have supervised training, that means you would need upfront to decide what is you're targeting. Who's going to decide? Would the human error have introduced some bias into the training process, and is there any way to reduce that? Thank you.
Yeah, great question. So it is a paradoxical thing where you're saying I'm training a model on people to improve what could be done by a person. And what that kind of comes down to often is that when we're taking a mine, what we're doing generally is we're averaging out the error across all the people. And what we can do is then look at how our models deviate from those people. And I can probably explain it best in an example. We did a model for a company where we had lots of different classes of veins. We started off with like 15 classes of veins. We ended up modeling 7 of them because they couldn't find 7 of them. So the process of going through that labeling process with the team actually found some holes in the model. You know, when I said I need 500 examples of this vein type and they couldn't find them, that tells you something about, you know, the issues with the labeling that's going on in the background. In terms of how do you validate good training data, when you present data back in the form, like I'll try to show you an example. So what we often do is show data back to clients in this kind of form where you say, here are all the little tiles of what you've called, you know, class A. You can usually find the odd ones out and remove them. So what happens is we start off with the labeling that's done by the geos, and then we predict a model, and then we give them the data back and say, take all the ones out you don't think belong. And then we do it again, and then we do it again, and then until everyone's happy that there's nothing coming back in any of these classes that not everybody agrees with. So it's a great learning process for the geos, and it presents the data in a way where we're grabbing imagery from all over the deposit and saying, here are all that class together, that allows you to see the things that are really hard to see when you're just in the midst of logging holes. So I think that it's a two-way process. We can help them get better at their labeling, and we can also make the system kind of average out errors so that you end up with an overall pretty good model. So I hope that was a long-winded way of saying great question, and it's complicated.
Anyone else in the audience? We've got a couple questions online, which I think, oh, actually quite a few questions online. I think you can see them, but for the benefit of the audience.
Yeah. I can actually see them if you want to. You're going to read them out, Katarina?
Yeah, I will read them out. That's right. Cool. All right. So nice presentation. I'm wondering if it is actually possible to classify minerals or alteration with just images. Some minerals are difficult to identify, even with micro XRF or LIBS.
Yeah, absolutely. Great question. The answer is, yeah, it depends on the mineral, and it depends on the way that mineral presents in the image itself. So I've shown you some examples of quartz on a grey background, really easy. If we were looking for some subtle alteration that was over the top of the core that wasn't visible in the visible light, then we wouldn't be able to find it. So it depends on what we're looking for. There are limitations. I haven't talked about it at all today, but we can also process better imagery in the sense that LIBS imagery, hyperspectral, we can process these same kinds of images using the same techniques. And obviously the better the image, the more we'll be able to see. So yeah, good question.
What is the picture resolution needed to use instant segmentation to classify minerals?
Yep. Cool. So there's one rule of thumb that will cover that, and most others, which is if you can't look at the photograph with your eyeballs and see the thing that you want us to go find, we can't find it. If you can, a model can be trained to find it. So the resolution is not one number. It depends on the thing you're trying to see, but they must be visible with the human eye in the actual image itself.
Have you tried classifying banded iron formation hosted iron ore? Yes. Without naming companies.
Yes, 1,000 times yes is probably how I would describe that. So yeah, definitely.
John Huntington is saying, very interesting. You've obviously looking at adding the info from hyperspectral sensors, HiLogger or CoreScan. Can you tell us something about that? Not just the hyperspectral data, but the interpretations produced by the hyperspectral mineralogical classifying software. Very good.
Yeah. So I think there's a couple of kind of parts to that. So we spent a lot of time classifying 1D wiggly lines as in terms of our consulting business, and in terms of the things I've talked about with deep learning, there's actually a lot of really good work that can be done using 1D deep learning models. and helping them improve classification for the actual mineral class. In terms of the actual hyperspectral image itself, the thing that this is really helpful for is, you're finding the mineralogy with the hyperspectral, but it's really hard to make sense of the things that are within the image. So you might find a vein and a beautiful selvage with the classification, but unless you actually know what a vein is in its entirety, it's sometimes hard to get an answer product out that says this thing is a vein of this type with this kind of selvage in it. So the way I kind of see them is kind of being yin and yang. You find the minerals that define that structure or vein, and then you can use deep learning to actually grab that entity out of the image and make it into an answer product. So that's probably what I would say to that. But John, I would say the thing that I think probably would be most interesting for yourself is that 1D deep learning models do really cool stuff with classifying infinite mixtures of hyperspectral wiggly lines. So thanks for the question.
We have another question. So that one is coming from Paul Greenhill, but I think we've answered it indirectly. He's asking about near infrared imagery that is informative with regards to mineralogy. So that's hyperspectral. Another question, core orientation. Can your system change the geo's failed orientation of the core in the trace so the core pieces fit better together?
Yeah, it's actually not the first time I've had that question asked. I would love the answer to be yes. I think it's a really difficult problem to solve. Often the way that the features will need to fit together, you can't see them well enough just from looking at the top to kind of be able to do that. I love the idea and I wish it was easier. We even thought about having a system where you could grab the piece and wiggle it and try to piece it back together. But when you're standing at the core trying to do that, it's hard enough when you can pick it up and twist it and try to make them lock. I think it's too hard, but I hope that I'm corrected on that at some point.
Cool. Mark Nopi is asking, great to see the practical application and the effectiveness of the tools. Approximately how many clients have been applying this technology and how long has this been available to the market, while appreciating that the applications are continuing to evolve and improve?
We've only been around probably doing this for about 2.5 years. And I would say that there's lots of demand in the industry for this type of work. There's lots of people selling, fancy scanning systems, but that they have 30 years of data sitting around in core photos that they need to get something out of as well. So there's certainly a lot of demand. I think companies are really interested in what they can get out of the imagery a lot more than they were previously. And to be honest, and I'll say this transparently, there's other people in the market offering things like this as well. So it's certainly a growth area. A lot of the scanning, system creators are doing stuff like this in part. And there's, companies like us that are trying to just digitalize the logging process. So so overall, I think it's really booming, and everyone's looking for that edge to help with their all body knowledge. So, why not look at your humble core photos and scanning systems can cost a lot of money. And I think historically they've suffered because people haven't been able to get the answers out of them. They've been getting drowned in data. And so this also helps with that.
Well, we're technically out of time and we still have a few more questions. If you don't mind, maybe I'll ask a couple more and then we'll let everyone go. Nathan Fox is asking, what can industry do during data collection to improve your workflows or reduce headaches? Example, image standardization. And what is the most useful complementary data set you routinely use?
Yeah, so on the first part, we usually give out core imaging guidelines to our clients to just help them, fix up the way they're imaging, even if they're doing a very basic imaging. Generally speaking, what we want as machine learning kind of practitioners is we want consistency of everything, and that includes consistency of the markup of the core. The other thing that's really important are unique markers on the core. So you're drilling a driller's break mark, or you're drawing some symbol that means something. Always draw it the same way, and you always use the same colored pen, like simple things like that. In terms of what's the most useful complementary data set, I actually think as a geologist, really detailed quantified mineralogy. So, you know, whether it's like Tornado or MLA or something like that, where you get this really detailed stuff kind of regularly down the core, we can then try to kind of interpolate that really good stuff out across the really cheap data. As the geophysicist in me would say, you definitely want downhole geophysics, televiewer, and all those fun things too. But yeah, it sort of depends on the application, I would say.
The one thing that you haven't really talked about is videos, although you mentioned them. Do you think one can use videos to classify particle size inside, let's say, a SAG mill? Yeah,
absolutely. And we've done some consulting projects kind of in that space. With respect to the technologies and the workflows I've shown you, a video is absolutely no different to an image. The video is just lots of images stacked together in time. So absolutely, you know, looking at flotation bubbles, looking at, you know, things running across a conveyor belt under a camera. People are starting to even look at borehole cameras that you look at the edges of the hole when you pull the drill strings out. Absolutely, all the things we've talked about here would be as applicable. If you go onto our YouTube page, there's a great video of us segmenting oysters moving down a conveyor belt. And so that I think has a lot of analogies to all the cool stuff you can do in processing with it.
And lastly, we have a couple more questions that are quite specific to what you are doing. So for instance, how long does it take to pick out the veins in the slide that you showed with the iterations? Like
yeah,
how long
so
did it take?
Yeah, so I think you're referring to the training. How long does it take to train a model like that? Generally speaking, we're in the orders of hundreds of examples of a vein, potentially to low thousands. The harder the vein is to see, the more training you're likely to have, and the more variation of that thing that it could exist, the more training you need to have. But there are lots of tricks to make lots of training data fast, so you don't have to sit there painstakingly and circle thousands of veins. There's ways to cheat our way to a bigger data set pretty quickly.
And I think that's partially answers the next question. Is there any crossover between models built for new deposits, or will a totally new model need to be built for every project that this is used on? Yeah,
great question. So when it comes to geotechnical models, the things that look about the way the rock breaks and the way the fragments of the rock kind of exist, they're very general. So you can use, you know, them across multiple deposits. When it comes to geological things, they're less general because rocks can look so different. So if you had lots of, you know, a certain type of deposit, potentially you would get good correlation across them. But generally speaking, we build the geological models from scratch each time, but the geotechnical models are actually building off a big general model that will have lots of different data in it.
Fantastic. Thanks so much, Brenton. Really appreciate your time and availability and being so detailed and carefully answering everything. Thank you so much. Just before we close off, next Friday, we are hosting Dr. Snezana Bajic, who is Deputy Chief Inspector of Explosive at the Resources Safety and Health Queensland Department. And we will confirm the topic of the presentation next week. Thanks again.
Great. Thanks, everyone.
Thank you.
Cheers.